Okay, welcome to day 2 aboard the Axiom. Today we're going to carry our study of magnetic forces a little bit farther than we did yesterday. So yesterday we learned that if a charge is at rest and placed in a magnetic field, it will not feel anything. This charge has to be moving in order to feel a force. We also saw that the charge had to be moving perpendicular, not parallel to that field. We had the formula to calculate the force magnetism. It's equal to the charge multiplied by how fast it's moving, multiplied by the strength of the magnetic field. We saw that we had to work in 3 dimensions. Remember, the x represents negative z direction, something moving away from us, and the dot represented the tip of an arrow moving towards you. That's the positive z direction. We saw that the magnetic force worked according to this hand rule. For negative charges, you used your left hand, and for positive charges, you use your right hand. And again, the field points in the direction of your fingers. Your thumb points in the direction that the particle is moving, and your palm will push on the direction of the force. Okay? So in this case, the force would be pushing down. When you have a positive charge, again, use your right hand. It's x's for the field, so our fingers would point in the negative z direction. Our thumb has to point to the right, so our palm pushes up. This particle would be pushed upward. Now this is where it gets really important. When this particle gets pushed up, the direction that you point your thumb also has to change. So you'll notice that as the particle deflects up, your thumb directs upward, and the direction of the force changes also. So the direction of the force is not constant. It will change as the particle goes off in different directions. The force will always be perpendicular to the direction the particle is moving. This will cause the particle to move in a path such that the force is always perpendicular to the velocity. Going back to what you learned last year, Newton's first law, objects in motion stay in motion in a straight line when there is no net force on them. An object moving to the left will continue moving to the left forever if there are no forces on it. We saw then that when you do apply a force, depending on the direction of the force determines what will happen to our object. So in this case, the object's moving to the left, the force is to the left, the object will pick up speed. In those cases, you use your equation of motion to track the object. If the object's moving to the left and the force is to the right, the object will slow down and come to rest. You use the same equations, except you make a negative acceleration. Then we have the case where the force is perpendicular to the direction the object was originally moving, but if you notice, the force stays pointing in the same direction. As the object deflects to a new angle, the force does not deflect with it. In this case, the object follows a parabola. In this case, we do the horizontal motion and the vertical motion as 2 separate problems. The horizontal motion is constant speed. The vertical motion takes place with acceleration. Here's our important one for force magnetism. This time, as the object deflects, the force deflects with it. It stays at a right angle to the velocity, and the object travels in a circular path. Hopefully you remember, acceleration in a circle is the velocity squared over the radius. If you need to, you can take that velocity and do distance over time, where distance is some multiple of the circumference of the circle. Okay, so using the magnetic force, 2 examples. One is the containment of matter or antimatter. So if we have matter in a magnetic field or antimatter in the magnetic field, we can get that object trapped in a circular path. And this way, if we have a vacuum chamber, that antimatter will never collide with the walls of the container. The object will constantly go around in a circle as the force changes direction with the motion of the object. To figure out what speed or what size circle you're going to get, we start with our force magnetism. We use it in acceleration equals force over mass. And then finally, we use it in our acceleration equals v squared over r to solve for the radius of this circle. I'd like you to try this problem. It'll be posted as part of your Google slideshow. Take a picture of your work and show me what you did. The second use of the magnetic force is in a velocity selector. We already learned about J.J. Thomson and how he had this glass tube with capacitors. He accelerated his charges and then he deflected his charges using an electric field. What I didn't tell you is we can also have a magnetic field. So you can see the X's represent the magnetic field. And what we're going to do is we're going to try to undo the capacitor's deflection by strengthening our magnetic field. And by doing this, we can get a magnetic field that's just strong enough to totally cancel out with our force electric. We start with the force electric. We do the same formulas we did last week. Okay, once you have your force electric, you then come over and look at the force magnetic. And what your goal is to try to cancel out the force electric with the force magnetic. So in this case, our electron would normally deflect up to the top plate because that plate is positive, but we're going to use a force magnetism that is pointing downward to try to cancel that out. So if you set these two forces equal to each other, you could solve for velocity, and that velocity will be special. It will be the only velocity that can make it through the capacitor undeflected. So ones that are moving too slow, this magnetism will be too small and they will hit the top plate. If the particles are moving too fast, the force magnetism will be too large and they will hit the bottom plate. Only the proper velocity will make it through the plates. So what I'd like you to do is to try to figure out what velocity would make it successfully through these plates. So I tell you the distance between the plates, 11 millimeters. I tell you the strength of the magnetic field. It is 0.05 Tesla. And I tell you the voltage on the plates is 600 volts. So try to work through this problem. Again, show me your work on paper, take a picture of it, and include it in the slideshow. And figure out what particle speed will make it through unscathed. Again, these particles are electrons. Okay, so figure out the speed that will make it through without deflecting up or down. Okay, that's it for day 2.